Identities enable us to write the same expression in different ways. When dealing with trigonometric identities, we're going to focus on how best to simplify them into something more manageable. And a lot of times that thing that's more manageable is a single trig identity. These are some of the trig identities that we've already run across, such as the cosecant of x is the same as 1 over sine x. Secant is 1 over cosine. Tangent is sine over cosine. Cotangent is cosine over sine. And our Pythagorean identities, sine squared x plus cosine squared x equals 1. Tangent squared x plus 1 equals secant squared x. And 1 plus cotangent squared x is equal to cosecant squared x. A lot of times the best way to simplify a trigonometric expression is by writing everything to be in terms of sine and cosine. So if there's a trig function in there that isn't in terms of sine and cosine, we're going to change it. For example, tangent can be rewritten as sine over cosine. So that's what I'm going to do. I'm going to rewrite it as sine over cosine. And remember that tangent is being multiplied by the sine. The next thing that I'm going to do is I'm going to multiply this together. So cosine t plus sine squared t over cosine t. Well, right now, if you don't recognize this, I have two fractions. I'm going to combine them into a single fraction. There's a nice little trick for doing that. The way that it works is you start in the lower right-hand corner and multiply up to the top left-hand corner. I'm going to get cosine squared t. The sign that you put next is whatever sign is between the two fractions. Then you multiply from the lower left-hand corner to the upper right-hand corner. And then for the denominator, you just multiply the denominators together. Well, I want you to notice that this was one of those Pythagorean identities. Cosine squared t plus sine squared t doesn't matter what order it's in because addition is commutative. It's just 1. And 1 over cosine t is the same thing as secant t. So now I've taken that trig identity and I've simplified it into something much simpler. And the only thing that I did was I used basic mathematical properties and basic algebra to do this. Everything that we're going to do in this section is using basic mathematics in terms of trig identities. Now let's do a simplifying by combining fractions. We know that we can't combine fractions unless they have the same denominator. And since these don't have the same denominator, in order to combine them, we're going to use that same process that I used in the previous problem. I'm going to multiply like this. I have to distribute, by the way. I'm going to get sine theta plus sine squared theta. And then I'm going to multiply up here, and I'm going to get plus cosine squared theta. And in the denominator, I'm not going to distribute yet. I'm going to leave that for a moment. And the reason I'm going to leave it is in case I can cancel something. The only time you can cancel things in a fraction is over multiplication. So I'm going to leave cosine theta being multiplied by the expression 1 plus sine theta. All right, now let's look at our numerator. Wait a second. That's 1. That's our Pythagorean identity. So I get sine theta plus 1 over cosine theta 1 plus sine theta. Now do you see why I didn't multiply out the denominator? These two quantities are the same, regardless of order, because addition is commutative. So they cancel, and you're left with 1 over cosine theta. And 1 over cosine theta is the same as secant theta. All that work to find out that initial expression was just equal to secant theta. Now, the reason that we're simplifying these expressions is because we're going to start to prove trigonometric identities. Proving means that we want to show that one side of the equal sign is equal to the other. Now, there is a process for doing this, and the process is either listed in the book or listed in your notes. What we do is we start by taking the more complicated side of the problem and simplifying that. This is the more complicated side of the problem. So I want to simplify that and make it equal to sine squared theta. So this is what I'm going to do. I'm going to do it the same way I did the previous couple problems, which was I'm going to put everything in terms of sine and cosine. So I'm going to rewrite secant as 1 over cosine. Then I'm going to combine that into a single fraction. Remember that that's over 1. So inside the parentheses, I'm going to get 1 minus cosine squared theta all over cosine theta. By the way, notice the order in which I combine those fractions. You have to start in the lower right-hand corner up to the top left. If you don't, you will get the wrong answer if the two fractions are being subtracted. All right, now I want you to notice that these cancel, and you're left with 1 minus cosine squared theta. Well, 1 minus cosine squared theta, let's go back to that trig identity, the sine squared theta plus cosine squared theta equals 1. If I solve this for sine squared theta, I find out it's the same thing as 1 minus cosine squared theta. So I can replace this with sine squared theta. And now I have made the left-hand side equal the right-hand side. When I do that, I like to put a check mark at the end to say, hey, I'm done. And that was all I had to do. This is really reminiscent of those two-column proofs. If you look at the problems in the book, they actually set them up in the two-column proof format with the actual reasons written out. Instead of writing out the reasons, I think the reasons are explicit in the actual problem because as long as you show the work that you've done, you've explained what you've done. All right, let's do another proving an identity. This time, the side that looks like it's probably more complicated is this one. Usually we think fractions are more complicated. So here's the deal. I want to simplify this so in the end it ends up saying 2 tangent x secant x. If it makes you feel better, but only if it makes you feel better, remember that tangent is sine over cosine and secant is 1 over cosine. So if you get 2 sine x over cosine squared x, you will have proven that both sides equal each other. But we don't have to do it that way. All right, since I have fractions, I'm going to start this way. Remember, lower right-hand corner to top left. Let's see, I should give myself more space here. All right, so when I do this, I get 1 plus sine x. When I do this, you're distributing a -1. So I'm going to get -1 plus sine x. And when I multiply the denominators together, I want you to notice it's in this form. We haven't seen this pop up in a while. Anytime you multiply together something in the form a plus b, a minus b, you just get a squared minus b squared. So when I multiply those together, I just get 1 squared minus sine squared. Okay, now let's do some simplifying in the numerator. I want you to notice the ones cancel. The sines don't cancel, but there are 2 of them, so I get 2 sine x. And the denominator, 1 minus sine squared x, well, that's just cosine squared x. Because if you take this identity and you solve it instead for cosine squared x, you're going to find out that it's 1 minus sine squared x. Now, in order to actually get the 2 tangent theta secant theta, what the book did was then they rewrote the problem like this. Because cosine squared x is really 2 cosines that have been multiplied together. And then they said, well, that's just tangent. And then they said 1 over cosine is secant. And that's where they got 2 tangent x secant x. Some of these problems can get a little bit more difficult because sometimes you have to add a little something extra in order to prove that the two sides of the identity are equal. So I want you to watch what I'm about to do. I'm going to work with the left-hand side because fractions are usually the complicated part. So what I'm going to introduce to this problem is the conjugate of the denominator. Do you remember what a conjugate is? The conjugate of the denominator is 1 plus sine u. The reason that I can do this is because I'm really just multiplying that fraction by 1, because this quantity here is 1. As long as you're multiplying by 1, you're not actually changing the problem. Okay, so now the numerator is going to become cosine u times 1 plus sine u all over 1 minus sine squared u, because if you remember from the previous problem, this is just in the form a plus b, a minus b. Now, I'm going to rewrite the denominator as cosine squared u. Now, I'm going to do a little bit of canceling because there's a cosine here and two cosines down here, so I can make this 1 plus sine u over cosine u. And now, I'm going to actually work this backwards, where I'm going to write this as two separate fractions. We've been combining fractions. Well, now I can actually go and write this as two separate fractions. So 1 over cosine u, that's just secant u. And sine over cosine, that's just tangent u. And isn't that what we wanted to start with, was secant u plus tangent u? So we just proved that the two sides are equal. And we did it by introducing the conjugate. And the reason I could do that is because really I was just multiplying by 1. Sometimes it'll behoove us to prove an identity by simplifying both sides. That sometimes it's just not easy to turn one side into the other. So we're actually going to work on both sides of the problem. And I'm going to start with the left-hand side of the problem. The 1 plus cosine theta over cosine theta. Well, I can separate that into two fractions because there's a single quantity in the denominator. So I can write it as 1 over cosine plus cosine over cosine. That's going to simplify into secant theta plus 1. Now I'm going to go and work on the right-hand side. Notice that the, I'm missing a minus sign here. Sorry about that. Let's get rid of that. Minus 1. All right. Notice that there's a tangent in the numerator and a secant in the denominator. So to work on the the right-hand side, I'm going to go back to those Pythagorean identities, because there's a Pythagorean identity that says the tangent squared theta is secant squared theta minus 1. And then this is just in the form a squared minus b squared. So it's secant theta plus 1, secant theta minus 1. And then those cancel, and you're left with secant theta plus 1, which is the same thing as we got on the left-hand side. So since the two sides are equal, they must be an identity. The last thing we're going to talk about is a trigonometric substitution. Substitute sine theta for x in the expression 1 minus x squared and simplify. Assume that theta is between 0 and pi over 2. Well, that just says if sine of theta is x, then under the radical it's going to become 1 minus sine squared x, or theta, whichever variable I'm using. 1 minus sine squared x, we just saw that. That's cosine squared theta. And, well, we know how to take the square root of x squared, it's x. So the square root of cosine squared theta must be cosine theta. And it's true because cosine theta is greater than or equal to 0 for the values of theta in question. And that was trigonometric identities.